So now we are getting to the discussion of group velocity, and what it means is that we are changing a little bit from plane wave to a situation the wave is not a total plane wave. What we mean is a plane wave means that you have a wave that fill out all space. And what is that is obviously not realistic. You can never have a wave that fill out all space. So it must truncate somewhere. So you have, say, you have wave propagate along a certain direction. So so you have mostly single frequency, so the wave is almost single frequency, but somewhere along the line you has to truncate this wave train. So it becomes instead of a infinite plane wave becomes a wave package. So somewhere it died down. So you can also like this, discuss this by envelope. So it's like the wave is oscillating within this envelope with almost like a single frequency. Okay, and you can talk about frequency or uh, wave number. It essentially the same. But in Jackson's discussion, we talk about the wave packet as the wave number first. So within this packet, it's like you have almost like a single wave number. The wavelength is almost the same. So you have some kind of case of zero mm, within within it, and then it died down. With, and the geometry is in Jackson's picture. Okay, and this is delta x. And now we're talking about this generic situation. So we are not just not just electromagnetic waves. So we actually simplify it to talk about a scalar wave with amplitude is the u variable. Okay. Um, that this u is propagating with a frequency omega. And now we're talking about the situation where omega can be a function of wave number, right? And uh, to actually have a good velocity different from phase velocity, actually this dependency is beyond linear. If it's just linear, then the phase velocity is the same as good velocity. But later on, we'll specify that. But we're just saying that something like that. And uh, we also consider the situation where you initially this u as a function x, so t is 0. You can express that as a integration of Fourier transform. So it's 1 over squared of 2 pi. And this is in Fourier, Fourier transform in space. So it's dk minus infinity, and the Fourier transform of the variable u in at t equals 0 is called a. Here it's actually called a, right? Basically. And then that this is Fourier transform in space, which usually right like plus kx. For Fourier transform in time, we use minus I. Space we use ikx. It doesn't matter. It's just a convention. And obviously, a actually depends on time also, but we'll ignore that for the time being. So, so this is the how you express u in terms of a. That a is the Fourier transform of this u initial u. So k is 1 over square of 2 pi. And x obviously is the propagation direction. And this 1 over square root of 2 pi is we use the convention that the coefficient in front of both equations is the same. So you put it in a symmetric form. So both of them has a 1 over square of 2 pi. That is actually easier to remember, so you don't, so you remember which one has a 1 over 2 pi, which one doesn't have any coefficient. This one is becomes dx. Now for calculating Fourier transform, you have a minus. Okay, so that's a Fourier transform pair. You remember you see Fourier transform before. Some of you haven't taken math physics yet, but you still know something about Fourier transform, right? So that's the Fourier transform pair. Okay, so now the idea is that this is initially is right that obviously actually can depend on T also, and then so in the general situation, x as a function of T will be again similar, but then a you're writing it as e to the I kx, and then a minus I omega t, but the omega now depends on t. So you put assuming that for each k component, it actually will move in this, evolve in time using this like a plane wave like dependency e to the minus I, except that now the omega, the wave frequency depends on what the wave number is. So that's functional form like that. And this AK is the same as this initial AK. So initially, you decompose your U into different wave number. Each wave number, it evolve in time according to this minus I omega t factor. Okay, and so that is what we use. This is a simplified model. I mean, in electromagnetic theory, there's complication that the wave equation is second order in time. This consideration is a little bit simplified. Jackson has in the next chapter, he will do slightly more general, including the initial condition, not just U, but partial U, partial T. So basically, it's like you're solving a Newton's second law problem, then you hit both the initial condition of the location and the velocity. You need two initial conditions. Likewise, in wave, second order in times derivatives, we need two initial conditions. But now it's just simplified. We just consider this one first, and to illustrate the concept of good velocity. Okay, so that is the next topic that I mentioned is the uncertainty principle, which apply in this situation, which is actually an important concept here. So you have this Fourier transform pair. It actually apply to more general situation. Any wave, Fourier transform pair of wave has the same. If any Fourier transform pair of any quantity has this property, so-called uncertainty principle. Although the term is from quantum mechanics, right? Obviously. You are taking quantum mechanics together with this. Is that are you? So you talked about uncertainty principle before. Did you divide that? Divide the uncertainty principle from. You did that. Divide that using Fourier transform.
No, we take the product. We don't divide it for that.
You divide that. Because,
If I enter value switching the transform, then I don't think we divide it for the answer.
I mean, if you want, I can divide it for you. Right? Only then you can spend the rest of this lesson and then discuss the good velocity later. So the I mean, the uncertainty principles, Jackson quoted this 7.82. So delta x delta k is greater or equals to 1. I mean, we can, this is, because I'm talking about the dividing it, because we already written down the Fourier transform pair in that the uncertainty principle to divide that is based on this two, and it's pretty straightforward. It's not that complicated, and because you're first you define this or measure this delta x, or and similarly you have a delta k also. So this is delta u. This is this one. But you talk about this a sub k. This would be also be somewhat a pulse in the k space. So this is k. This is a, and there will be a delta k. Usually it will be something like that. You have a wave package in k in the x space, in the physical space, and then in the Fourier space you will also have some kind of pulse, some kind of profile for the a for the Fourier transform, right? And then we can define this delta x and uh, delta k by, like we can define the delta x squared, or some kind of a measure. It's like you can define, let's say you multiply by u by x, and then multiply by u, and this is dx, and multiply by over the whole range of variables. And actually it should be these are, this can be a complex function. So and the way that if it is a complex way, this can also be a complex function. So you can write it as a complex magnitude square, and then multiply by x, and then integrate x squared and integrate over the whole range. But to get the correct delta x dimension, you need to divide it by wave squared. Right? That's you can define something like that as a measure of this width of this wave packet. And similarly for delta k, you multiply by k squared, yeah. And then this now k is a profile, so you have k squared and dk, and likewise you normalize that by a squared. Okay, so now we can use some property of Fourier transform, and the first property is the so-called Percival theorem. The Percival theorem is basically saying that for this Fourier transform pair, is u square x is the same as a square ck. Have you heard about it, or you learned about it? This Percival theorem. You haven't seen that? Yeah, this is a property. It's based. It's not difficult to prove. Basically, you're just substitute like this, substitute back to here. I mean, when you have u and like u this U squared is just U times U complex quantity. HU, you're using this Fourier transform expression in here. This is, and then the complex quantity, you put it in here, and then you do the dx, and then you then be able to show that it should recover to change it to this one. Okay, and it take a few lines of derivation, but for the time being, I don't have time for that one. Okay, let's just assume that this is you pick up from a math handbook. This is called Superposition theorem for each transform pair. I mean, defined by this symmetric notation. Otherwise, you will have 1/2 pi at one of these either left hand side, one right hand side. If symmetric, it's good that the positive theorem doesn't have coefficient. So it's like that. Okay, so let's continue. Hopefully, we can finish that today. And now, what we want to consider is the numerator. You multiply each together. And what it means, you have to multiply delta x squared and delta k squared. So this is that, and then multiply by the respective denominator. So this is but this one you multiply by this over the other side, and this one you multiply this the other side. But by the perseverance, they are actually the same. So basically, you multiply by minus the square of this one. Okay, and that equals to the new multiplication of the numerator, this one and that one. Square, square, and no, minus e square, a square. Okay, you see that basically this numerator multiplied by this numerator. This one multiplied by the denominator, multiplied by this one, multiplied by this denominator, except the two denominators are actually the same by the perseverance theorem. Okay. Now we are using the perseverance theorem again, but now we consider the Fourier transform pair, not the U and A, but the partial U partial X. So like if you consider this, you take the partial derivative, partial X. Then what happens is pull out this minus IK here. You pull out IK, right? So basically multiply by IK. If you do this operation, you multiply by IK here. So it means that IKA is the Fourier transform of partial U partial. Is that okay? You can see that. So, and likewise, you can use the perseverance theorem. So whenever you have IK in here, and put in here, so that becomes a IK magnitude square. So when you take the magnitude square, I doesn't matter. Basically, K square, A square, which is this one, K square, A magnitude square. And now the U is not U, is this partial U, partial X. So change that to partial U, partial X. Now again, perseverance theorem, but this changed to partial U, partial X. But the X, because this is dk, perseverance theorem changed it. Is that okay? Now apply another math property that's called the SWOT equality. So basically, this is all square term. This is all square term. But the idea is it will be small or equals to the magnitude square. Putting everything, taking everything out, say this will be xu And for this one, you would take the complex conjugate out. Partial U. And the idea is that partial U partial X magnitude square is partial U partial X times partial U complex conjugate partial X, which is this one. So you can pull either one of them out. And this is called the SWOT inequality. I suppose you haven't heard. In math physics, we'll go through that. I forgot which chapter. Maybe before the complex conjugate chapter. When we talk about complex, on top we talk about dot product between in the function space. So that you can see that the why this is so. This is you have all these multiplication, right? But if you are instead multiply them together and take and integrate them and take the square, it should be smaller than you individually square them and then integrate them first. Because when this thing has sign, right, it's actually complex, can be complex. When you multiply by them, this is most likely into the positive and negative. And then when you integrate that, it will cancel. There will be cancellation. That should be smaller than you take each one and take the square of that first and integration and multiply together. Okay, so that's the SWOT inequality. Now we are about to finish the derivation. So this is now you can use the integration by part because you are partial X. You have to do an integration by part, and the first term is everything together. Or you can actually put this inside that first, because this is you use complex conjugate. You can actually change it to magnitude square, and then divided by. It's like x squared over 2 and ddx x squared, and then pour 2 and ddx. Okay, this is just holding you together before you do the integration by parts. So now the integration by parts is you have a 1/2, put the 1/2 over. Actually, 1/2 is within the square, so it's 1/4. And then you have integration by part is x squared minus infinity to infinity and minus and u squared and then the dx, which is just 1 u squared. Magnitude squared. This is just evaluate plus or minus infinity, which is 0 because we are assuming that the u will decay at infinity. So that's 0. It's localized wave packet. And now this is exactly the same as this one. Right. This one is exactly the same. And then there's a square, this is square. Right. And so this means combine this with the delta x squared, delta k squared is smaller than 1/4. And you take the square root, magnitude delta x, magnitude delta k is small. This is the uncertainty principle. No, God, yeah, I see like that picture. Okay, I got the sign. I got the sign wrong. This is greater than. This means that, I mean, this is because you have all the cancellation, usually you get a smaller value. This is square every time. This is what inequality is like. This is greater than, this is greater than 1/4. Greater than 1/2. Okay, so that is the uncertainty principle. Okay, so with that, what Jackson talked about, I mean, this is a derivation, but it's important to get a sense of how these things relate to each other. Say, we already said that this is mostly like a plane wave, except that you have a very long wave packet. And according to this uncertainty principle, now delta x is really large. So that will allow you have a small delta k, because delta k will be something divided by delta x, right? It's greater or equal, but most likely it's equal. So delta k will be something 1/2 delta x, and delta x is large, so delta k will be small. In this case, you can say that, and physically it's what we see that because it's mostly single wave number. So this is center case of 0, right? And then the width of this line in the Fourier transform is very small. The delta k is small. But then the other situation, sometimes later, if you consider a wave that is with a very short pulse, or even may not have the structure inside, but just a short pulse in x, then the Fourier transform in k will be very broad. When delta x is small, then you have a delta k with all right, so that's the understanding from the uncertainty principle. So they kind of go inverse to each other. So when you have a delta k, delta x is large, then delta k would be small, and delta x is small, then delta k is large. That you have that kind of relationship. And this is for any wave or even any Fourier transform. This kind of property, because in this derivation we are just using property of Fourier transform of some localized quantity. And that applied for generally for Fourier transform also, or Fourier transform pair. Okay, so likewise you can change the delta t, and then that becomes a delta omega. Delta t and delta omega satisfies the same relationship. Okay, so that's part of this section. We'll finish that section